start talking about main topic, which is the these kind of stochastic processes. And in particular, our focus is going to be moving more on something which is called Brownian motion. It's also called the Wheeler process. There are lots of ways to approach, say, Brownian motion. But let's first talk about how all this story began actually. Okay, so there was a guy, Robert Brown, he was a geologist. So he observed that if you have a liquid, say like a water, okay, and if you, for example, throw a pollen particle, okay, into this water, what will happen that this pollen particle is going down. Okay, so we know that what pushes us to go down actually, so it's gravity. But an interesting thing happens that when this pollen particle is going down, it's not going down straight, but it's wiggling it. So it goes down, but with a wiggle. Okay? And Robert Brown was not able to understand it actually, why that happens. Okay, he understood that. Okay, it's going down, the particle is going down, the particles are going down due to the gravity. But why you have this wiggly, what do you call the process? Then, in 1905, which is like the miracle year for Einstein, which kind of made him famous actually. Okay. So in this miracle year, Einstein wrote 5 papers actually. Okay. One of the papers was on his famous theory of special relativity. Okay. It was not popular, it was not a popular paper at that time because no one believed it, because he started questioning time, which was very weird. But there was another paper that Einstein wrote, and that paper was about the existence of atoms actually. That okay, atoms do exist actually. So he kind of theoretically demonstrated actually that yes, you have the existence of the atoms actually. And then in the same paper, he basically formulated the mathematical nature of the Brownian motion actually. Okay. So what was previously observed, okay, was not explained mathematically. So what he did, so he kind of explained mathematically the nature of the Brownian motion. That why particles are, if they are moving in a wiggly manner, that why they are moving in this manner. Okay. In 1900, there was a guy called Louis Bachelier. Okay. So he wrote a thesis making the first complete mathematical treatment of the financial markets. He was the guy who kind of gave the first mathematical market of the financial market. And then he also, this Bachelier also tried to explain, not really explain, but he assumed that the stock prices, okay, the prices of the stocks basically, they are random, obviously, but he assumed them to be that, okay, these stock prices basically follow Brownian motion actually. Okay, and based on it, he made some predictions. He introduced that yes, in a certain situation you can get rid of the risk. I mean, if you can price an option, so option is something that can allow you to, hedge the risk, substantially. But what he proposed, Bachelor proposed that, okay, I know that option is something that is going to help us to hedge the risk, but I don't know that how to price it actually, or what should be its premium. Okay, and this thesis was re-explored in 1960. Okay, by something which is called the Policy-Wilson actually. So like I think this work was not published actually. It was just a thesis, sitting back in the, it was just in, it was just so Policy-Wilson kind of found this thesis in a laboratory, and then he realized that what a brilliant work this guy had already done, and that in 73 led to the what you call the revolution in finance, what you call this 1973, which is the pricing of the option actually, the Black-Scholes equation, and hence the Black-Scholes formula. Okay. Anyway, so these were the two guys who kind of Bachelor and Einstein, who kind of tried to tackle to mathematically explain actually that what do we mean by Brownian motion and how to mathematically explain it. Okay. So let me just give you a brief idea of what does Einstein did actually. So he said, let us assume that you have a crystal clear tube, okay, of certain length, okay, and in that you have a clear water actually. So it's a clear tube containing the crystal clear water actually. Then, so imagine this location is x equal to 0 at time t equal to 0. Imagine I am injecting the ink into this crystal clear, tube containing water. I know that this ink is gradually going to spread over the entire tube, or maybe the portion of a tube actually. But this spread is not going to be something deterministic actually. So it's going to be something random. So if we say talk about a one particular particle which was kind of injected, here, the question is that can I say something sensible about its location and about its future, okay, in a coherent way actually? The answer is, so that's what Einstein tried to answer actually. So what he assumed that this particle, or each of the particle of the ink, is basically doing Brownian motion actually. It is going to follow a random path and going to reach somewhere within the tube and eventually going to stabilize actually. So tube 0, ink injected, okay. So let's assume that U, that is uxt, denotes the density of the particle. So it depends the density of particles, okay, at x, so position x at on time t. Okay, this is what. So initially, when you are injecting the particle, what should be the density of the particle? So what should be the good function that can describe, the density of the particle? So if I want to set up an initial condition, what should be that initial condition? What do you think? So if this x is any one of, this location actually, okay, that you, So obviously in the beginning you don't have any particle inside it actually. Okay. While if this x is 0, then the entire mass of the ink, okay, is really concentrated at a point actually, at one single point in in the face of this tube actually. Okay. So how you can represent it? So you can say that it's gonna be the Dirac mass at 0 actually. Okay. So ux0 is the Dirac mass at 0. So what is the Dirac mass? So you all know that. So it's gonna be 0 everywhere. At 0, it has a huge value, explodes actually. Okay. And we also know that its integral from minus infinity to infinity is 1 actually. Okay. So we know all of its properties. Okay. So in other words, initially the entire mass of the ink is concentrated at one single point actually. Okay. Alright. Then what Einstein assumed, it assumed that the probability that a given particle is going to move from a position x to x plus h. Okay. So the probability that the density, the density of the ink, probability of the density, what do you say? And that ink particle move from probability that the density of the particles that move from x to x plus h is say f of say h tau actually. So currently the density is uxt, okay, and I'm interested in, so for example, computing the density at that point actually, and I know about the probability of a particle moving from this position to this position is basically this probability distribution. Okay. Then how can I compute the density? Okay. So what he assumed that the density of the particle at position x at time t plus tau, okay, t plus tau can be explicitly written as the convolution of two functions actually. Okay, the convolution of two functions, which can be explicitly written as minus infinity to infinity, and u say x minus h x minus. By the way, I'm assuming that at instant you have time t, and at this instant you're going to have, the time is t plus tau. Okay, so when the particle are, for example, moving, the time is passing. You are going to expect that less particles will be here, while the more particles are going to move ahead. Naturally, that's what is going to be an assumption. Anyway, so if you take, for example, so it's a convolution of ux h t with the probability distribution that is f of h tau and d. Okay, this was the data what you call one of the assumptions of his work actually. That if I'm interested in computing the density of the particles at position x at time t plus tau, this can be computed as the convolution, okay, of the density that you inherited from the previous position, okay, at time t with the probability of gaining new particles. And then I can do what? I can, next thing is that I can, expand, I can write a Taylor expansion of this uxt. So if I want to write, I can write a Taylor expansion of it. So the Taylor expansion of it is going to be u minus, say, uxh plus 1 over 2ux x h squared and so on and so forth, and h tau and not dy but dh actually, moving with respect to h. I'm using a different notation than this notation. So imagine if I ignore all these terms, okay, because the higher powers of f are going to contribute less and less, then what would be this integral explicitly? So this guy is going to turn into three expressions. So so let's think about each one of the expression actually. Okay, so minus infinity to infinity, I have u f h tau dh. Okay, but while obviously the u is a function of x and dh, it's a function of x and tau. Okay, so what it would be? So this expression is independent of h, so you can pull it out. Okay, and then you are doing what you are, integrating a density function from minus infinity to infinity. Then you expect it to be un. Okay, because u does not involve such, so you can. What would be this guy? You can do the same with it. So I can pull out, for example, this ux. So the second integral, for example, minus infinity to infinity. So you have this ux h and f of h tau dh is going to be what? So, anything. I mean, if you wish, I can pull this guy out. Okay, the real thing is that I would like to talk about this guy, like what this guy is going to be. This guy, first of all, this f, it's a probability distribution, but what is going to happen is that we can assume, okay, the symmetry. So at the back of your hand, for example, you can have that this is something like the normally distributed. It's like normally distributed at the back end of it. I know that normally distributed random variable has a PDF that is symmetric around origin. So this guy is symmetric. So if this is symmetric and h is multiplied with it, so can you say something sensible about this integral? This must be 0. So if f of h tau is same as f of minus h tau, for example, okay, if this property is satisfied, then so this is like, okay, here's the thing. You may assume that this is like an even function actually in h, and you have a h multiplied with it. So what would be the nature of this entire function? Odd. Odd function. So if you are integrating an odd function from minus infinity to infinity, you expect it to be 0. Okay? What would be this guy? The third term is uxx. Okay. So this would be, say, h squared f dy. Okay. So what Einstein assumed that, I'm assuming that, so this is like the expectation actually. When you think about it, that's expectation. Well, this is variance. Okay. That's the variance roughly of the random quantity. So what does Einstein made an assumption about it, that this variance is proportional to the time tau actually, on which everything is depending. So f by tau dy is something that is proportional to the tau actually. So this expression would grow the more and more time when it passes actually. So hence if you equate it, so you can have a constant here. So that was another assumption that it made, that that this integral, okay, you can also interpret it as a variance, okay, is linear in its nature actually over time. So therefore you're going to get this. Now if you have this assumption, think about what you're going to get, the final picture actually. Okay, so on this side you have ux t plus tau. I have ux t plus tau. Okay, and this is equal to u plus 1/2 uxx by 2. Okay, and the integral that is going to be d tau. Right? This is going to be d tau. And okay, so this is going to be d tau. So what you're going to do, take this term on other side and divide by tau. So you're going to get uxt plus tau minus uxt, and you divide everything by tau. Okay. What you're going to get here, you're going to get d by 2 uxx plus the higher order term involving tau. Okay. Or you are ignoring the higher order term. And now, if you take, for example, this tau goes to 0, then this will become 1. So this is going to be ux, okay, d over 2. Ut, sorry. Ut is going to be ut, d over 2 and uxx. So what is this? What is this? Making something like this.
Equation. Transport
That's
equation.
heat equation.
Heat equation.
That's heat equation. Okay. Did a force on PD last time. I forgot about heat equation. Really? So it's heat equation. Okay. So what does this means, that this predicts that the way, so if I have a metallic rod, okay, and you are connecting it to some heat source actually, then the way heat diffuses into the rod, okay, is the same way, the particles are going to diffuse into this clear water actually. Okay. These wiggly things are going to diffuse in the same way into this water actually. Okay. Just a review of the work that Einstein did actually. Okay. That's how people started talking about it. In fact, Einstein also gave a precise, description of the d, that what this d is going to be. So he said that this d is going to be RT over NA and F, where R, you can say that it's a gas constant, T is the absolute temperature, F is the fraction, and NA is what you call the Avogadro number actually. Okay, so Avogadro number. So remember Avogadro number? The Avogadro number is the number of molecules that are present in a 1 mole of something actually. Okay, so 1 mole of something. And this was the motivation actually that allowed people to this guy Avogadro to predict the number NA actually, that what should be the number of atoms. So later, based on this paper, okay, this guy Avogadro gave this number precisely, precisely that 6.6 into 10 raised to power 23 particles in a mole actually. Anyway, आज याद आते हैं सारे. किधर कर रहे हैं काम?
HF लॉट.
अच्छा. आज हमको क्या मिल सकते हैं?
आज नहीं कह सकते.
Let's see how it is. Anyway, so something that was observed by Brown not only been explained by in 19 of Einstein, but he also basically explained things based on the Brownian motion, which is, for example, the diffusion of the ink particles, which are randomly moving into the crystal clear water. All right. So let's move towards. इनसे क्या दिया? इसको थोड़ी देर बंद कर सकते हो तो कर दो, otherwise देर बात कर देना थोड़ी। ठीक है जी। Physical motivation. Alright, so consider random walk actually. Okay? Consider random walk. So what
wasn't that also random walk?
was also random walk actually. But what I would like to do now, I would like to take a random walk, and I did the same in my first discussion actually as well. That I mean, if you, for example, consider the random walk, okay, and you join them with, for example, linear line, you linearize it, and you scale it down. Okay, then that scaled process is going to satisfy some properties actually. It's going to satisfy some properties. So I'll quickly recall, that is stuff that I was talking about 2 minutes ago. So consider random walk. So what do you mean by random walk? You can, at the background, you can keep this example in your head that imagine you are playing this coin tossing game. On each bet, either you are going to get $1 or lose $1, okay? And Zn represents your gains after the n games activity. Okay? Then Zn can be written in many ways. So one way could be that, okay, what were your gains at time n-1 plus the outcome, where Ln is the outcome of the nth game actually. Okay? The outcome of the nth game. Or you can also write this as that this is the sum, so 1 to n, of the all outcomes of the ith game factor. So, where the Li is, say, plus 1, minus 1, okay, with probability, p and say 1 minus p actually are half or 1/2. Okay, and we know that it's a random walk. What immediate things about you can observe about the random walk? So what are the key properties that this random walk is going to satisfy? So number 1, okay, in the beginning, what should be your gains? 0. Okay. Sure, almost surely you can begin with 0. Secondly, imagine imagine you have, so what would be the expectation of the gains? Maybe let's think about it. What would be the expectation of LIs? 0. So it must be 0 as well. So that if the expectation of, the gains of the ith games are 0, then the expectation of Zn must also be 0. Okay. So that's the second observation you can make about it. The third observation that you can make about this a random walk is this. Okay. That if you, for example, take 4 moments, so 0, so j, k, and say m and n. So imagine you take the 4 moments actually. Okay? J, k, and k can be less than or equal to